Alright everyone, so welcome back. So in the last video we gave an introduction to limits and went through a couple of examples of how we want to solve them. So primarily algebraic manipulation, but one of the things that we kind of glossed over in the last video was how exactly we solve limits. So the particular issue was there were points where I would go and plug the limit point into our expression to get a final answer. And today we're going to go over when, at least some of the time, where we're allowed to do that. And we'll also introduce a few rules for limits. Okay, so the standard kind of questions that we've had so far. And today we're going to really focus on the third one. So we're going to go and elaborate on some more tools for finding limits. Okay, so here are the main rules that we have. So we're going to suppose that we have two cases. We have two assumptions. We have one, we have the limit as x is going to a of f of x, and that limit is equal to L, and then we have the limit as x goes to a of some function g, and that is equal to m. We'll also assume that k is a constant, little m is an integer, and little n is a positive integer, where m over n is in lowest terms. So something like you couldn't have m be 6, well n is 2. Okay, so the first rule that we have is a sum and a difference rule. So if we take the limit as x goes to a of f plus or minus g, that is L plus or minus m. So in other words, what this is saying is that the limit of the sum, so the limit of f plus g, is the sum of the limits, L plus m. And the same is true for the difference. For a product, so we look at the limit as x goes to a of f times g, we get L times m. So in this case, the limit of the product is the product of the limits. When we're given a constant multiple, so we're given the function k times f, and we look at the limit as x goes to a, we're able to pull the constant multiple out in front, and we would just get k times L. For a quotient, provided that m is non-zero, the limit as x goes to a of f over g is L over m. So in this case, the limit of the quotient is the quotient of the limits. The power rule is maybe a little bit more tricky just because we need to make sure that everything is well defined. So if we are looking at the limit as x goes to a of f raised to the m over n power, that is going to give us L raised to the m over n power, provided that if n is even, L is bigger than 0, and if m is a negative number, L is non-zero. So if m were negative and L was 0, that would mean that we would be winding up with a limit heading off to infinity, and as we said last time, those limits do not exist. In the event that L was negative and n was even, you would be looking at square roots or maybe fourth roots or sixth roots or so on of negative numbers, and those are purely imaginary numbers which we'll say also do not exist. So for as far as we're concerned, everything needs to be a real number. Okay, so we can go through a few examples. So the first one that we're going to look at is a polynomial in general. So suppose that we have f of x is some polynomial. We're not necessarily concerned about how long it is or what the numbers are, just some polynomial. Okay, and we'll look at the limit as x goes to c of f of x. So we'll take the limit as x goes to c of an x to the n plus an minus 1, x to the n minus 1, and so on. Well, the first thing that we can do is we can go and apply our sum or difference rule, depending upon whether the an's are positive or negative, and we can write this as the limit as x goes to c of an times x to the n plus the limit as x goes to c of an minus 1, x to the n minus 1, and so on. Then for each of those limits, we can pull the constant out in front. So we would get an times the limit as x goes to n plus an minus 1 times the limit as x goes to c of x to the n minus 1, and so on. Then the next thing that we can do is go and apply the power rule. So what we have here is we just have x to the n's. So we have a limit as x goes to c of x to the n. Our power rule says that we can switch the order of taking the power with evaluating the limit. So that'll tell us that the limit as x goes to c of x to the n is the limit as x goes to c of x all raised to the n. So we'll do that for each of the powers. And then what we said the last time is that if we have the limit as x goes to c of just x, what we're asking is, as x goes to c, what is x behaving like? Well, x is behaving like c, so that tells us that each of these places where we have a limit as x is going to c of x is just going to be a c. And then our limit as x goes to c of that constant a0 is just a0. So what that tells us is that the limit as x goes to c of f of x is an times c to the n plus an minus 1 times c to the n minus 1 plus each of the terms down to the end. And in general what this says is that for any polynomial, if you're looking at the limit as x goes to c of f of x, that's just f of c, which says that whenever you have a polynomial, you can go and plug in x equals c and you're done. That's the answer. Okay, so now let's go and look at a rational function, so a polynomial divided by a polynomial. So here what we'll say is we have the limit as x goes to a of x squared plus x plus 4, all divided by x cubed minus 2x plus 7, and we'll assume that a is a number so that x cubed, or so that a cubed minus 2a plus 7 is non-zero. So making that assumption, from our quotient rule, we're able to switch the order of doing the division and evaluating the limits, because the denominator polynomial will not be 0 by assumption. So then that will tell us that we'll have the limit as x goes to a of x squared plus x plus 4, all divided by the limit of x going to a of x cubed minus 2x plus 7. And then particularly what this says is we're now looking at the limit as x goes to a of two polynomials. And what we just said is that whenever you're looking at the limit as x goes to, in this case, a of a polynomial, you can just go and evaluate the polynomial at, in this case, a. So what we'll wind up with is a squared plus a plus 4, all divided by a cubed minus 2a plus 7. And that leads us to this very nice result. So it says that if f and g are two polynomials and a is some constant, then the limit as x goes to a of f of x is f of a. So in other words, when looking for the limit of a polynomial, you can just go and plug in the point x equals a and you're finished. And if you have a rational function, so long as the denominator polynomial is not going to be 0 at a, the limit as x goes to a of f over g is just f of a divided by g of a. So in general, whenever working any problems, once we've reduced our setup down to looking at something at just limits of polynomials, we're finished. In effect, we can go and plug in the point x equals a and we're done. Okay, so let's continue on with these remaining 6 examples. So we'll look at the limit as x goes to 2 of the square root of 2x plus 1. Now, the square root of 2x plus 1 is itself not a polynomial, but what we're going to do is use the power rule to go and get down to looking at the limit of a polynomial. So our power rule said that if, so we assume that the limit as x goes to a of f is L, and the limit as x goes to a of f raised to the m over n power is L to the m over n. So in our case, what we have is m is 1, n is 2, and our f of x is this 2x plus 1. So as x goes to 2, the limit of 2x plus 1 is going to be 5, because we would have a polynomial, we're allowed to just plug in the value. So here by the power rule, we're going to be able to switch the order of taking the limit with the power operation, because 5 is bigger than 0. And what that'll tell us is that we'll get the square root of the limit as x goes to 2 of 2x plus 1. We now have the limit of a polynomial, so we can plug in x equals 2, and we get a final answer of square root of 5. Okay, in the next example, so we have the limit as x goes to 0 of square root of x squared plus 4 minus 2, all divided by x squared. Now, in this case, what we see is that the denominator is going to 0, so our denominator function is going towards 0. So, and at the same time, we could also see that the numerator is also going to go to 0 if you just plug in x equals 0. So in this case, what we're going to do is we're going to go and use the conjugate that we mentioned 2 videos ago. And the main reason here is that we want to move the square root. So we're going to move the square root down to the denominator, in effect. Because what we have is this x squared plus 4 underneath the square root minus 2 is 0. But if we take x squared plus 4 plus 2, we'll get something non-zero. For these kind of problems, it's maybe not the most obvious thing to do, but as you work more and more of these problems, you gain intuition about how you want to go about solving these problems. So this is the first thing that we're going to do here. So what we're going to do is multiply the numerator and denominator by the square root of x squared plus 4 plus 2. And that way, the numerator, we get a sum and a difference, which when we multiply it out gives us a difference of squares. In this case, our squares are going to be x squared plus 4 and a minus 4, so that way the constants go away in the numerator, and we're just left with an x squared in the numerator, which will very conveniently cancel with this x squared that's going to be sitting down in the denominator. So when we cancel all of those away, we're left with the limit as x goes to 0 of 1 divided by the square root of x squared plus 4 plus 2. So at this point, all we've done is algebraic manipulation. Now we're going to start using some limit rules. So what we could see here is that as x goes to 0, this denominator is not going towards 0, so we can use our quotient rule. And we can write this as 1 divided by the limit as x goes to 0 of the square root of x squared plus 4 plus 2. And then what we'll do is we'll use the sum followed by the power rules, and what we'll see is we have a polynomial here, x squared plus 4. As x goes to 0, that polynomial is going to go, that limit is going to be 4. So we're going to be able to switch the order of taking the square root and evaluating the limit. So what we wind up with in the end is 1 over the square root of the limit as x goes to 0 of x squared plus 4 with a plus 2 outside. And then because we've reduced our problem down to looking at limits of just polynomials, we're going to be able to plug in x equals 0 and get a final answer of 1/4. Okay. So for the next example, we want to look at the limit as x goes to 1 of the square root of 1 minus x squared. Now, in the previous examples that we've had with square roots, we've just been able to switch the order of taking a square root with evaluating the limit. If we just blazed ahead and did that here, we would get the square root of the limit as x goes to 1 of 1 minus x squared. We would say, well, we have the limit of a polynomial, we'll plug in x equals 1, we would get the square root of 1 minus 1, or 0. But remember, this power rule only applies in this case when L is bigger than 0, because here n is 2, so n is even. So the power rule doesn't actually apply in this case, so we need to think about what's going on to figure out what the limit's going to be. Well, what we've said for a limit to exist, if we went back to our definition of limits, is that we need the function under consideration to be defined for every x value near our point, in this case 1, except possibly at 1. So we'd first want to ask, is this function actually defined for all x values near 1? And in fact, it's not. So for example, if we take x values that are slightly bigger than 1, no matter how slight, just any x value bigger than 1, 1 minus x squared is something negative, because you take a number bigger than 1, you multiply it by itself, you will get something bigger than 1. So 1 minus something bigger than 1 will give you something negative, and you're going to be taking the square root of something negative. But when you take the square root of something negative, you get an imaginary number, and we've said that those do not exist. So in this case, the function square root of 1 minus x squared is not actually defined for any x value bigger than 1, so our limit does not exist. Okay, for the next for the next example that we're going to do, we need to talk about what's called the absolute value function. So the absolute value function is just seeking to measure how far away your number is from 0. So just a distance, really. So what you can do to rewrite anything with an absolute value is if the thing inside the two vertical bars is something positive, the absolute value of x is just x. But if you have a negative number or a negative quantity, the absolute value of x is minus x. So for example, suppose that you are looking for the absolute value of 4. Well, that's just 4, as we would have from right here, because 4 is positive. But if you're looking at the absolute value of minus 3, the absolute value of minus 3 is 3, which is the same thing as saying minus 3. So in this case, your x would be minus 3, you'd have a minus 3, and just get 3. Okay, so we want to look at the limit as x goes to 0 of the absolute value of 3x minus 1 minus the absolute value of 3x plus 1, all divided by x. The first thing that we could see is that if we just plug in 0 for x, we would get 0 divided by 0. So again, that tells us we can't just say 0 over 0 is undefined and say the limit is undefined. We need to go and do some algebraic manipulation, which is what we're going to do here. So the first thing that we can do is we can say, well, let's go and try and resolve what's going on with these absolute values. So for the first one, we have the absolute value of 3x minus 1. Well, as x goes to 0, the 3x part is going to be going towards 0. And we're still going to have this minus 1, so it's going to say 3x minus 1 is going to be negative as x goes towards 0. And over here, as x goes towards 0, 3x plus 1 will be something positive. So it tells us that the absolute value of 3x minus 1 is going to be minus 3x minus 1. And the absolute value of 3x plus 1 is going to be just 3x plus 1. So we'll go and write those absolute values as so, and then simplify. And when we simplify, what we see is that we get a plus 1 and a minus 1. Those go away. We're left with minus 3x minus 3x all divided by x. We have minus 6x all divided by x, and that limit's going to be minus 6. Okay, for our next one. So for the next one, what we see here is that we're looking at the limit as x goes to a of the absolute value of x minus a, all divided by x squared minus a squared. So here what we need to do is we need to split things up into looking at a left and a right limit. And the reason for that is because for x values that are bigger than a, the absolute value will be written differently than for x values to the left of a. We'll see what that means just in a moment. So here, if we take an x value that's bigger than a, we have x minus a. If x is bigger than a, we take away a, we get something positive. So x minus a is going to be positive, and we'll write the absolute value of x minus a as just x minus a. Our denominator, we have a difference of squares, so that factors into a sum and a difference, and we'll cancel off the two x minus a factors. Then we'll be left with the limit as x goes to a of 1 over x plus a, and we get 1 over 2a. We'll also assume a is not 0, because otherwise we run into problems. Okay, but then the left side limit, we're going to take x values that are less than a, and then when we take something that is less than a and subtract away a, we get something negative. So we'll write the absolute value of x minus a as minus the quantity x minus a. Our denominator still factors as a sum and a difference, and we'll cancel off the x minus a factor in the numerator and denominator. And we're now left with the limit as x goes to a from the left of minus 1 over x plus a, which is going to be minus 1 over 2a, because again, in this case, we're looking at the limit of a rational function. But because 1 over 2a is not going to be minus 1 over 2a, that'll tell us this limit will not exist, because the left and the right side limits are not the same. And we said last time that if that a limit's going to exist if and only if the left and the right side limits are the same thing and the value of this limit. So because the left and the right side limits don't agree, our two-sided limit does not exist. Okay, so then the next example that we want to do is we want to look at the limit as x goes to 0 of x times cosine of 1 over x. Now before, we'd looked at the limit as x went to 0 of cosine of 1 over x. And what we said is that the limit as x goes to 0 of cosine of 1 over x did not exist because that function wasn't going to settle in on any particular value. And what we'd like to do now is look at x times cosine of 1 over x. And what we see is that none of these 5 rules that we've used so far work. And the reason for that is the assumption for each of these 5 rules is that the limit as x goes to a of f of x and the limit as x goes to a of g of x both exist. For us, the limit as x would go to 0 of cosine of 1 over x does not exist. So if we wanted to go and try and apply the product rule, would probably be the clear one to try. It doesn't actually apply because the limit in this case of x going to a of g does not exist. So what we need is a new rule. And what we're going to use is what's called the squeeze theorem. So this rule says, suppose that we have a function f that is always less than or equal to g, which is always less than or equal to h. If the limit as x goes to a of f is equal to the limit as x goes to a of h is equal to some number L, then the limit of x going to a of g of x is equal to L. So in other words, what we're saying is that as x goes to a, this function which is always smaller, which is always less than or equal to g, is going to some number L. And then this function that's always bigger than or equal to g is also going to the same place L. So g has nowhere to go except L as x goes to a. And here's maybe a simpler illustration for what's going on with this squeeze term. So we can think about the trash compactor scene from A New Hope. Right, so in that one, our heroes have just gone and rescued Princess Leia, and in their escape, they wind up in this trash compactor, and all of a sudden the walls start closing in on them. Well, so what's happening here is you have the right wall and the left wall would come together, if not for some ingenuity from Han, Luke, and Leia, and I guess also Chewie. The walls would come together and squish our heroes. And that's kind of the idea of what's happening with the squeeze theorem, is that you have the left wall and the right wall are going to come together and squeeze the function. Okay, so what we want to do is we want to see how the squeeze theorem is going to actually work in practice. Particularly on this limit as x goes to 0 of x cosine of 1 over x. So the first thing we'll do is we need to come up with a function that's always going to be smaller than the function we're concerned with and also bigger than the function we're concerned with. So what we can start by saying is we know cosine of 1 over x, it's always going to be in between minus 1 and 1, except at x equals 0, but we're not really concerned about what's happening at x equals 0. And then we could multiply everything by x. So we'd say that minus x is less than or equal to x times cosine of 1 over x is less than or equal to x. Just minor concerns maybe about whether or not x is positive or negative. So if x is going to 0 from the right, we'll have that minus x is less than or equal to the limit as x goes to 0 from the right of cosine of x cosine of 1 over x, which is less than or equal to the limit as x goes to 0 from the right of x. But then we're looking at the limit of polynomials for minus x and also x, so that's going to tell us that the two bounding limits are both 0, and that tells us that the limit as x goes to 0 from the right of x times cosine of 1 over x has to be 0. And then we could do the same thing for left limits. So we could take the limit as x goes to 0 from the left of x, which will be less than or equal to the limit as x goes to 0 from the left of x cosine of 1 over x, which is less than or equal to the limit as x goes to 0 from the left of minus x. Again, limits of polynomials kick in, so we have 0 is less than or equal to our limit as x goes to 0 from the left of x cosine of 1 over x is less than or equal to 0. So the left limit also has to be equal to 0. And now what we have is the left and the right limits are both equal to 0. So it tells us that our two-sided limit, the limit as x goes to 0 of x cosine of 1 over x, has to be equal to 0. So one thing that's really nice about a squeeze theorem kind of problem is that you never actually work with the limit of the thing you want to find. Typically, you're working with limits of simpler functions. So in this case, instead of actually working with the limit of x cosine of 1 over x, we were only looking at the limit of x and minus x, which are simpler things to work with. So that's one of the nice things about the squeeze theorem. Okay, so I think that gives you all the tools you need for the moment for solving some introductory limits, and there will be a worksheet in YO courses on these kind of limits. And then in the next video, we will be going over what happens when we start bringing infinity into things. Okay, and I will see you all then.